All right, welcome back. Hello, everyone. Today I'm going to talk about the Gram-Schmidt process. Okay, this video is part of the singular build decomposition SVD the video series. Okay, so I'm going to cover. I'm discovering all the background, the mathematical background of SVD from scratch, and then I'm going to cover some advanced mathematical theory relating to SVD, and we'll see applications. Okay, all right. So the what's the Gram-Schmidt process? So Gram-Schmidt process is an algorithm for producing an orthogonal or orthonormal basis for any the non-zero subspace of the Rn space. Okay, so to to figure out what the Gram-Schmidt process, we'll see some simple example. Okay, so let's get into the simple example one. Okay, so let's say W is a space spanned by two vectors x1 and x2, and you see x1 and x2 are given like this. So 3 by 1 just matrix, I mean column vectors. Okay, so we see that x1 x2 are vector in three-dimensional space, right? Okay, but I don't think W is the R represent the R3 space, because there is only two the vectors spanned by two vectors. So anyway, so to construct the orthogonal basis v1 v2 for W, okay, so we gonna set first one, we're gonna just set the v1 as just one of the vector, but normally we choose the first vector x1. Okay, so we choose the x1 as v1. Okay, and then next step is to construct the vector which is orthogonal to v1. Okay, that's a strategy. Okay, so since the W is a space spanned by two vector x1 x2 in R3, so we see that W must be a plane in R3. Okay, so here's a plane right there at W. So then let's say this is x1, then we choose that x1 as v1. Okay, this is v1 right now, and then we're gonna find out the orthogonal projection of the vector x2 onto x1. Okay, all right. So and then we see, then that's kind of shadow of the x2 vector x2 onto the x1, right? So that's a projection of x2 onto x1. Okay, so we have seen this one in vector calculus, right? Okay, so now we're gonna set the new vector by subtracting that vector from the x2. Then we're gonna get that the vector colored red. Definitely, this is the orthogonal to vector x1. Okay, so we set this one that the vector colored red, which is orthogonal to x1, as v2. Then v1, v2 gonna be orthogonal, right? So, and then we can say that those two vectors must be orthogonal basis of the plane W. Okay, that's a strategy. All right, so then how can you compute the orthogonal projection of x2 onto x1? I'm sure that you know about this already, but let me write it down. The formula, that's going to be inner product of x2 and x1, or we can say dot product of x1 and x2. Okay, so but in a linear algebra, we call this one as inner product. This is the notation of the inner product. Okay, but this is nothing but dot product in calculus. All right, so and then the square norm. Okay, or we can say this is the square of the magnitude of x1 vector. Okay, either one just fine. Okay, so let me say the square norm square. Okay, so this is L2 norm square. So times x1. Okay. All right. So now then, what? See, this is nothing but x2 dot x1 over x dot x1, right? Because the L2 norm square is nothing but x1 dot x1. Or you can say the square of the magnitude of x1 is nothing but x1 dot x1. Okay, that one just fine. All right, and then now we to get the numbers, we put the numbers of x1, x2 into the formula. Okay, so that also gonna projections. Okay, so we get this. That's a p vector p. Let's say this is a vector p. Okay, so we subtract the vector p from x2 to get the vector color the red right there, which is orthogonal to x1. So that's going to be 0, 0, 2. Okay. So now then v1, v2 going to be orthogonal set of non-zero vectors in a W, and then dimension of W is 2. Okay. So if the number in orthogonal set number of the vectors is equal to dimension of W, then we say that that set, orthogonal set, must be a basis set. Okay, orthogonal basis set for W. Okay, so now let's see example 2. Okay, so we haven't seen in example 1 is quite simple, right? Okay, but example 2 a little bit more complicated than example 1, because you see we have one more vector right there, and then number of the entry, each vector is not just 3 but 4, right? So 3 vectors are given, but this is a linearly independent. Why? Because so let's show that these 3 vectors are linearly independent. Okay, it means that what? When you're writing the vector matrix equation, this is let's say this is a matrix. Okay, x1, x2, x3 is just a column vector. So this is going to be a 4 by 3 matrix times, let's say this unknown vector c1, c2, c3 is equal to 0. So that vector. Okay, so that x1, x2, x3, that set is linearly independent. It means that the matrix equation A, let's say this is A, okay, A times C, unknown vector, is equal to 0, has only trivial solution. So trivial solution means that 0 vector. Okay, so it means that the null space of that matrix A must be equal to set of only 0 vector. Okay, so then what? So let me show this. How can you show this one? So I will just find the reduced row echelon form of the matrix A. Okay, so you can see that we got the 3 pivot columns right there. Okay, and then the last one is 0, 0, 0. So it means that x1, x3, x1 through x3 must be a basis set for a subspace W of R4. Okay, so if you don't get it, just please watch the matrix system and then the reduced echelon form. Okay, video. So let's see here. Solution. Let v1 is x1. Okay, the strategy is pretty much the same as the example 1. Okay, so we set the first the vector as v1. Okay, and then we find out the space generated by that vector x1, or you can say v1. And so this is v1. This is a v1 right there, which is x1. Then the space generated by the v1 going to be just straight line, right? Okay, along that vector at v1. Okay, so W is simply a straight line in R4. Okay, now what you're gonna do, we're gonna find out the second vector v2 by finding projection of the x2 onto the vector at v1. Okay, and then we find out what the vector, which is the orthogonal to the x1 by subtracting that projection vector from the x2. So v2 going to be x2 minus projection of x2 the onto the v1. Okay, so we know the x1, the entry numbers for entry of the x1, so we know v1, right? Also we know x2. So we can find the projection of x2 onto v1, and then we can find the v2 finally, right? So now that you see the v2, it turns out that v2 is like this. So every entry has the fraction, has the form the fraction. So, but personally, I don't like the fraction form. So to get the integer form, I just multiply by 4, which means that I just scale. I want to just scale the vector v2 by 4. So we scale v2 to simplify. So we just we set v2 as 4 times v2. Just scale it by factor of 4. So we got this. So v1, v2 going to be orthogonal, right? So we say the v1, v2 is an orthogonal basis for the subspace w2. So what does w2 look like? Because you know, w2 is you know, the space spanned by x1, x2. Because let's say this is x1 right there. This is x1, which is nothing but the what, x1, and x2 is this one right there. Anyway, so v1, v2 is this. Definitely v1, v2 must be orthogonal right there. So anyway, the w2 gonna be what, a plane, right, in R4. Okay, so there is no way to visualize R4. Okay, so the let's say just, you know, R4 is contain the w2. Okay, well, we cannot see R4, so and then there is no way to, you know, the visualize R4. So okay, anyway, so definitely we know that v1, the you know, the what, the w2 spanned by x1, x2, or we can say v1, v2 must be a plane, right? So what you're gonna do, step 3, we find out a vector which is orthogonal to v1 and v2. Okay, and then what you're gonna do, we're gonna use x3. So x3 is like this, and then we're gonna find the projection of what? See, let's see. We find the projection of the x3 onto w2. Okay, actually this is w2, right? Okay, so this is typo. It should be w2, right? Then we got the that, you see that the arrow vector we colored yellow, right? And then we subtract the that projection from the x3. Then we're gonna get the vector which is perpendicular to w2. So you see that green vector, that's the vector obtained by the subtracting v2 from x3. Okay, that's a v3. So you see the v3 is perpendicular to plane w2, subspace w2. But anyway, okay. Now then, okay. So how can you find the projection of x3 onto the w2? Okay, this should be w2. Okay. So now the how can you find the projection of x3 onto w2? Then we find out the shadow vector of x3 onto v1, and then find another shadow vector of x3 onto v2. Okay, so that's what we're gonna do. All right, and then we adding them up. We're adding them. That's gonna be projection of x3 onto w2. Okay. So keep in mind this. So now, so that we doing that, we're gonna get this number. And what can you? Before going further, let's take a look at the basis theorems. So let's say the space vector space V be a p-dimensional vector space, and p is greater than or equals 1. Then any linearly independent set V1 through Vp is automatically a basis for vector space V. Okay, so it means that as long as the linear independent set, as long as the number of vectors is equal to the dimension of the vector space, then that linearly independent set must be a basis for the vector space V. Okay, and the second statement is this: V1 through Vp such that V is the span of V1 through Vp is automatically a basis for V. Okay, so it means that this as long as the vectors the a vector set span the vector space, okay, then that set must be a basis set for vector space B. Okay, so now applying the base theorems into the problem, example 2, then V1, V2, V3 is an orthogonal set, right? And then thus linearly independent, makes sense. Otherwise, the V1, V2, V3 not going to be an orthogonal set, right? So then W is R3 because it was defined by a basis of 3 vectors. So by basis theorems, so V1, V2, V3 must be orthogonal basis for W. Okay. So V1, V2, V3, what does that mean? V1, V2, V3 is an orthogonal set. Right? It turns out that, well, we construct the V1, V3, V1 through the V3 as orthogonal each other, right? So this is orthogonal set, right? Okay. And then since they are orthogonal set, so they must be linearly independent, right? And the number of vectors is equal to dimension of W, right? And then by the basis theorems, that one must be on orthogonal basis, okay? So the Gram-Schmidt process, here's the, okay, let me summarize the Gram-Schmidt process. So given a basis x1 through xp for a subspace W of Rn, we define V1 as x1 and the V2 is x2 minus the projection of x2 onto V1. Through this Vi, we define Vi as is equal to xi minus sum of, what is this? This is a projection of xj onto vj, and j equals 1 through I minus 1. Okay. Then V1 through Vp must be an orthogonal basis for W, and then the span of x1 through xk must be equal to span of V1 and Vk. Okay. All right. So that's for today.